Good morning, everyone, and thank you for joining me today. I am pleased to present our finding and experience from operating a furnace with a 100% pellet burden. A bold move rooted in innovation, optimization, and sustainability. Let's begin with the background and objective. Incidents start uh, with some planned shutdown of Sinter plant, which leads to a drastic reduction in body composition and leads to a situation where transitioning from blend of pellet sinter to 100% pellet burden in blast furnace. These raise the questions about slag control, which is supposed to be most challenging, especially during controlling the slag basicity, the cohesive zone, and the dust management. Our goal was to test 100% pellet operation for more than 1 month and fine tune parameter before making it permanent. Now, coming to the trial period outcomes, as you can see during the trial, uh, it is closely monitored the gas utilization and top gas temperature. These were the key indicators of furnace performance and help align operational parameters for optimized efficiency and heat distribution. Now, it is very important to see the challenges unless until we differentiate the composition of the sinter and pellet, the challenges will not, we could not able to trace the challenge. Hence, it is essential to share the compositional variance of the burden component. One of the most striking difference between sinter and pellet as shown in the slide is it lies in the composition. As I have mentioned, pellet offered higher Fe content, as it is mentioned around 66% and more than that, compared to 61% in sinter. Of course, it's higher in compared to the usual context of sinter and a much lower AFEO. Now the basicity dropped from 2.19 to 0.23 as it is shown in the slide, necessitating the use of direct slag formers like limestone and BOF-slag. So this also gives us a learning that when we concentrate on a body matrix of higher pellet percent, basicity becomes a challenge. And we have to acquire some basic components like LD slag or limestone to add on to tune our slag basicity. Now, coming to the operational transition, which is also very important point. The transition is not abrupt as it is shown that first the palette, this is also a learning point that when we have a transition to a higher palette, then we need to go through a small quantum first and thereafter ramping is required so that you can tune off the distribution, the utilization, top temperature and the wind acceptance, as well as we will have a time to see that what's going on with the quality which whose reflection is getting translated in our dust catchers and the clarifiers, that is consequently we can say the sludge outcome, and it can also guide us that what sort of quality of pellet we are handling in the furnace. So the transition is not very abrupt. Transition when we ramp up, it's quite needed that we should go from a small quantum to higher quantum, as it's shown also in the slide that pellet use increases from 30 to 100% more than 40 days. So we have to keep blast volume between a stipulated band, which also gives us which also ensure us the stability of our blast furnace processes. Also, it is needed that the target slag basicity lies from 9.5 to 1.1, and it is also achieved with a reductant rate of 460 kg per ton hot metal, as it's shown. Now coming to the slag management, which is supposed to be the biggest challenge. As expected, slag volume dropped significantly to around 200 kg per ton hot metal. However, alumina content rose due to reduced slag volume, because this slag volume has come down drastically, which also is well anticipated by the operator when we go from sinter burden to pellet burden, and that too also towards 100% pellet use. Now sulfur distribution improvement is seen, uh, which is and also shown in the slide. So we can say that the temporary FU spikes during cold working reminded us to stay cautious and adaptive, as it is also shared, this information is shared in the slide. Now coming to the most important aspect of efficiency, that is gas efficiency. Efficiency saw a notable boost that it has hit around 54%, well above our baseline of 50%. So we can say that during these uses, 4% of utilization has gone up, and this gives us a lot of benefit in terms of fuel fuel saving. And it is also seen that the post shutdown, the top gas profile shifted to an inverse V shape, which came with a trade-off like increased wall hit losses due to changes in cohesive zone due to the higher pellet use. So now coming to the environmentally, the trial uh, feedback. So we can say that environmentally the trial was very encouraging. The flue dust level remained very stable. The sludge generation increased slightly, which in the next presentation we will share the intricacies of this flue dust level, and its hidden fact, we will be shared in the next presentation, as this will go very long. This suggesting a need for enhanced cleaning capacity. On the material side, we recommended a 1:1 limestone to BOF-slag substitution ratio to maintain basicity without overloading the system. So in conclusion, it can be said that the transition to 100% pellet was smooth and strategically successful, which is evident from the top temperature gradual trends, utilization trends. This gives us also a feedback that this transition was very stable, and with a 20% drop in slag volume and a reductant rate of 460 kg per ton hot metal was the final outcome. However, limestone substitution must be carefully balanced to avoid unintended impact on coke rate and post transition. It's crucial to keep an eye on cohesive zone stability to preserve furnace health.